Okay, welcome. There's my topic, and let's just do it. The dilemma with these back to basics talks is how basic to get. And I'm going to try to start at the very beginning, what I think is the very beginning of this topic, but go really fast. Just stop me if there's anything that you need me to dwell on, but otherwise I'm going to sail along for like 30 slides to get to the real meat. So what are the uses for const? Well, one of them is to define symbolic constants, but it turns out now in modern C++, const_expr is often a better choice for doing that. Also, to define immutable data, something where you say, I want this piece of data to never change. Well, it turns out const_expr is also kind of bumping const aside here as well. So what's left? What's left is being able to prevent the modification of data that's already modifiable. And turns out that this, in my opinion, is what const really is useful for in modern C++. That's what we're going to be focusing on. It's mostly, oh, stand in the light, okay. It's mostly when you're doing argument passing, especially when it involves pointers and references, and that's where we're headed with this. So just the high level idea is using const is good hygiene. What it does is it turns potential runtime errors into compile time errors. And the nice thing about that is it's really hard to ignore them when they're compile time errors. And so the consequence is that what you wind up is that const helps you write better interfaces, things that state more clearly what they intend and protect themselves against misuse. Now, in contrast, const_expr really doesn't play a role in this. Const_expr has to do with turning runtime computations into compile time computations. So we won't be talking all that much about const_expr. It's mostly const. Now, one of the things I hope to accomplish here is to make it that more programmers will be using const proactively. Because I teach a lot of people, a lot of experienced programmers, and the feedback that I often get is, yeah, we know we should be using const, but we're a little bit skittish about doing it because we're not sure that we're doing it properly, and that we have occasionally thrown const into existing code and regretted it. And so, in fact, the reality is that retrofitting code that doesn't use const so that it does use const properly is kind of rough. And so what we want to do is get in the habit of using it proactively, which means do it as you're designing and coding and plan ahead. And I hope to encourage you, more of you, to do that or to give you the tools, if you're already doing it, to help persuade your colleagues to do that with you. Okay, so what's the basic part is what most of you already know, which is that when you use const to define objects, what you're doing basically is saying, I want these objects to be non-modifiable. Now notice I throw in the colloquial sorta, because I don't want you to get too wedded to this yet. It's going to take most of the hour to get the truth out about what const really means. But a good first order approximation is to say that a const object is something that you can read from but not write to. So there you can read, number is a constant integer, you can read from it but you can't write to it. Message is an array of constant characters, you can read from the individual elements but you can't write to them. Most of you know that, so let's just go on. Here's an interesting property, is that because const objects can't be written to, your only chance to give it a value is at the moment of birth, when it's created. And so C++ imposes a semantic requirement, which is that you must initialize every const object, mandated initialization. So for example, here we have the declaration of a const integer called upper bound. That's an error because it lacks an initializer. Now in contrast, you can put extern on a declaration like that, and that means it's not a definition. It's just a declaration. The actual definition of limit is somewhere else, that's okay to leave the initializer off. And then here's the way you're used to seeing it most of the time is declaration with an initializer. Now there's this important idea that's both in C and in C++ called the constant expression. There are numerous situations where we need to be able to provide things like array dimensions. And notice there that that declaration for the integer x, the first local variable inside foo, that's an unacceptable declaration because it has a dimension which is non-constant. The 17 for the dimension of y, that's perfectly okay. And there are several other, half a dozen or so contexts in C++ where you're allowed to use an expression, but it has to be a constant expression, like for example, a bit field width. Constant expressions can involve operands and operators. It's not just a single integer literal or a single identifier. There can be operations in there as long as the whole thing can be crunched at compile time. So a constant object initialized with a constant expression is itself a constant expression. So you can, that definition for level is perfectly legit. It says level is a constant integer initialized with a constant value. You can then use it to form more complicated constant expressions, like 2 times level plus 1, and that's still an expression that can be evaluated at compile time. That's a perfectly legitimate array dimension. But surprisingly, const objects don't always result in constant expressions, and the reason is because you can initialize a constant object with a non-constant initializer. And when that happens, the compiler might defer the initialization until runtime. So it's a value that's not computable at compile time, and so here's a situation where you can use a constant object in an expression and find that the compiler will complain because level in this context is not a constant. It's a constant object, but it's not initialized with a constant expression, and so it itself is not a constant expression. Okay. So this is where const expr comes in that a const expr object definition gives you a guarantee that the initializer is itself a constant expression. There's a mandate that if you declare something as a const expr object, the initializing expression is an error if it is a non-constant initializer. So the resulting type, in this case, for example, on the last line there, min is a const expr object. It's const, but the presence of const expr there instead of const says, and now give me an error if the initializer isn't a constant expression. So my colleague Steve Dewhurst is around here somewhere, and he introduced me to this nice concept, which is const expr is conster than const. And so as a general style guide, you should prefer const expr to const for defining symbolic constants. But having said that, we're going to largely set const expr aside because its role is not in parameter passing the way we're going to be talking about it very shortly. Now, before I go on, I want to talk a little bit about some of the syntactic issues. First one is, I'm not going to say much about volatile here, but I do want to note that const and volatile are close cousins. Together, they're known as CV qualifiers because anywhere in the syntax that you can throw const, you can throw volatile, or you can throw both. And so collectively, they're called CV qualifiers. And although, again, we're not going to talk much about volatile, one of the interesting side effects of this discussion is that once you learn the type conversion rules involving const, you know them for volatile as well. They're very close parallel. Interestingly, const expr is not a CV qualifier. You can't use their const expr everywhere that you can use const, and vice versa. So for example, Well, I'll give you some examples in just a moment. That's where I'm headed. Now, as we just saw earlier, declaring const objects of an arithmetic type is pretty straightforward. The real interesting and complicated stuff happens when you start mixing in pointers and references. And so I think that my experience in teaching this is that a lot of people don't quite understand the syntax of declarations, let alone how const plays a role in there. And it's interesting, most books and articles try very hard to avoid telling you what the underlying syntactic truth is, and it turns out it's only going to take us a few minutes. So let's just do it, and you'll see it's remarkably straightforward. I don't quite know why so many of my colleagues try to avoid covering this, because it's really pretty straightforward. So here it is. What I'm going to do is give you a bunch of sort of basic insights into the structure of declarations in C++. And I'm not pulling out grammar rules, and we're not getting to that level of detail, but this is a pretty accurate model of the way the compiler views things. The first thing is that every declaration for an object or a function has two main parts, and I'm using color highlighting to make it a little easier for you to recognize it. The first part is called the declaration specifiers, and the second part is called the declarator. I believe declarator is a completely made up word. It comes from the grammar in the C language. And the name being declared, the thing that's in the center of that declarator, is known as the declarator ID. That's a little bit of syntactic notation I'm gonna introduce here. Now the declaration specifiers, you know what these things are. But the important thing is they break down into two broad categories, type specifiers and non-type specifiers. Type specifiers are things like int, unsigned, long, double, or user-defined types. In this case, like string, or even the instantiation of a template like vector int. Those are all things that could be type specifiers. The non-type specifiers are the other keywords that handle things like storage classes or function properties like virtual, keywords like inline, typedef. Those are the non-type specifiers. Now, so the declarator is the declarator ID, the thing being declared, possibly surrounded by operators. And again, you know what those operators are. There's stars, square brackets, the ampersand for reference, the double ampersand for R value reference, and so on. Notice that there's a precedence here. And this is one of life's mysteries. It's surprising how few C and C++ programmers know this underlying truth about declarations. And here's what it is. It's that when presented with a declarator like that, how do you know whether it's a pointer to an array or an array of pointers? The answer is very simple. It's the square bracket has a higher precedence than the unary star. And so it follows then, the winner is, it's an array of pointers. Now these are the exact same precedence rules that exist in expressions, and all of you know about those, right? If I were to write an arithmetic expression like a plus b times c, and I would ask which has a higher precedence, the multiply or the add, you'd all say multiply, right? But then when you show people a declarator and say, is that an array of pointers or a pointer to an array? If they answer correctly and you say, I ask then, how did you know that? Let's do a little, how many of you already knew that the precedence rules applied here? Can I just see a show of hands? Yeah, I'm seeing about 10. Yeah, there's probably 80 people in this room. And that's very typical. It's like duh, right? The precedence rules are a fundamental part of expressions. And declarators are expression-like things that behave according to the precedence rules. So now you are members of a very select community within C and C++. Now, parentheses, of course, give us a little bit of a problem because they play two roles, both in expressions and in it's actually three roles in expressions because you have the function call operator, you have grouping, and you also have casting, a form of casting that we never use anymore, right? As a function call operator, the parentheses will follow the declarator ID, and they have the same precedence as a square bracket. But as grouping, the grouping will enclose the declarator, and that has the highest precedence of all. For example, this is a declarator that says f is a function that takes an int and returns a pointer. If you want it to be a pointer to a function, you put parens around the f and the star. So again, I'm using color to show you the part in gold there that's the grouping parens. And you can tell those are grouping parens because the declarator ID is on the inside. You can tell that the red parens there are the function parens because they're after the declarator ID. It's very simple. Okay. Bear with me, I'm almost to const. Okay, it is related. Okay, so the type specifiers in the declaration specifiers modify other type specifiers, but the non-type specifiers, it turns out, go directly to the declarator ID. So again, the big thing for you to understand is what's the difference between a type specifier and a non-type specifier? Because, for example, there, the unsigned and the long are modifying int, but static is directly modifying x. The entity in that declaration has the property of being static is x. So you read this as x is a static array of pointers to unsigned long integers. It's a very inside-out kind of process, but it's what it is. It's not that bad. And this is as bad as it gets. Now, this is one you might not want to know, but it is what it is. The order of the declaration specifiers doesn't matter to the compiler, so those are the same thing. So are those. Okay, you can think of it as the compiler comes in there and just scoops up all the declaration specifiers and dumps them on the table and sorts them out like Lego bricks. It's that it doesn't care what order you write them in. And of course, this opens for very heated discussions, right? Okay. This one is interesting. Const, turns out, is a type specifier like long or unsigned. It's not like static or extern, it's like long or unsigned. And this one never occurred to me until many years ago. I wrote an article for a now out-of-print publication explaining this stuff to the readers of that publication. And I got back a letter from somebody who had written this stuff in the right-hand column, expecting const to behave like static. And so I thought it was worth a moment to point this out. It never occurred to me that it was anything but that const modified the int, but it's worth mentioning. It's a type specifier. And here's the other twist, is the const and volatile are the only symbols in C++ that it can appear either as declaration specifiers or in the declarators. So here, whether you say int const constant, the important thing, as marked by the bold vertical line, is to know where the declaration specifiers end and the declarator begins. When you're on the left-hand side of that line, the order doesn't matter. When you're on the right-hand side, the compiler is pretty inflexible about what it will accept. There's a little bit of wiggle room, but not much. Here now the const is in the declarator. It's not modifying the int. It's actually modifying the star, the pointer. So when the const appears to the immediate right of a pointer operator, it's actually modifying that pointer. It makes what was a pointer into a const pointer. And so here are just a few examples. This is a pointer to a constant pointer, or a constant pointer to pointer. It's actually a constant pointer to a, let's be explicit, non-constant pointer. Now the star and the const are separate tokens. How you space things, that's style. All of those 4 different variations are acceptable to the compiler. I happen to have a preference, and it's motivated by this, is that because the const is modifying the star to its immediate left, and in fact, grammatically, it's known as the const pointer operator, and the star const has the same precedence as the star by itself. So I remove the space between the const and the star just to reinforce that notion. So here is my simple advice on being able, see, I haven't yet really told you what const means, but assuming that you have a rough idea of what const means, if you want to be able to write a declaration where const is in the right place, here's a little bit of advice. First, write the declaration as it would be without const or volatile. And then simply place const or volatile to the immediate right of the type specifier or operator that you want to modify. Here's an example. Suppose what I want is an array of n const pointers to volatile uint32s. What you start out by doing is get rid of the const and the volatile. Just write an array of pointers to uint32s. That's it. Start there. Okay, now make a little space so that there's room for the const and volatile. And since I want the pointer to be const, I put the const to the immediate right. I want the uint32 to be volatile. I put the volatile to the immediate right. And as the Brits like to say, Bob's your uncle. You got it right. Okay, what about const expr? Let's just spend a moment on this, because it is what it is. Now you know that to the left of that separator, the order doesn't matter. Const char, char const, same thing. It's true with const expr, because const expr is a declaration specifier. So const expr char, char const expr, same thing. But these are not equivalent. And the reason here's what the equivalence is, drum roll please. That's it. Okay, now what's going on here? Well, const expr is not a type specifier. It's a declaration specifier, but it's a non-type specifier semantically, which means that it behaves more like static. The thing that is const expr here is x. So that means that from a type standpoint, not regarding the initialization, but just from the standpoint of the types, that const expr declaration is equivalent to this. It's making x a constant pointer to an unsigned long int. X is an array of constant pointers to unsigned long int. Okay. Now just another basic but noteworthy point, the address of operator preserves constness. If you have that I is a non-constant integer, its address yields a pointer to non-constant int. If you have ci as a constant int, taking its address yields a pointer to constant. This also happens with the implicit conversions regarding arrays. There is this conversion known as the array to pointer conversion in many contexts, not every context, but in many contexts where you use an array, the compiler will implicitly convert it into a pointer to its 0th element and use that for the rest of the expression evaluation. Same thing happens with string literals. That double quoted XYZZY really has type array of constant character. If you use it in an expression, it is quietly converted to pointer to const character. So these conversions preserve constness. Okay, with that background, now let's look at some various uses for const in pointer declarations and talk a little bit more about what they mean. So now you know those two are equivalent. That p is a pointer to a constant t or a t that's const, however you want to say it in English. And what does that mean operationally? What it means is that you can modify P. You can store new values into P, but when you use the expression star P, you can't write to it. You can read from it, you can't write to it. You contrast that with this one. P is a constant pointer to a T. So that means that P itself is a constant pointer to a non-constant T, but star P is non-constant. So you try to assign to P itself, that's an error. But you can assign to star P. And then finally we have this one. You can have that P is a constant pointer to a constant T. And it means that by itself, P is a constant pointer, and star P is a constant T, which means attempting to assign to either P or star P will be rejected by the compiler. So now let's look at some conversion rules, and this is really the heart of our discussion. All of that syntactic stuff was leading up to this, which is the real substance. So here what we have is a pointer P, it's a pointer to non-const, and a pointer PC, which is a pointer to const. And we have two functions, WP, which is short for once pointer, and WPC, which wants a pointer to const. Now clearly, these are going to be okay, because if you have a function that wants a pointer and you give it a pointer with no constness in the equation, that's going to work. And if you have a function that wants a pointer to const and you give it a pointer to const, everybody's happy. Here those declarations are again. This is the challenging question. Can I call once pointer and pass it a pointer to const? That involves a conversion of converting a pointer to const into a pointer to implicitly non-const. How about this one? I have something that wants a pointer to const, and I give it a pointer. Can I do that? And the answer is one of them will compile and the other one will not. But this is just a special case of a broad category of problems, which brings us to the title of our talk, which is, don't memorize this. I want you to be able to reason it out, because it rears itself in a whole bunch of different scenarios, not just involving pointers, but involving references and member function calls and things like that. And so think of const as a promise. In other words, you can apply ethical reasoning to the semantics of const, which, I'm sorry, if you're a sociopath, you're out of luck, but assuming that you're not, this should work. And so let's apply the ethical reasoning to an imaginary conversation between K, the keeper of some thing called X, and B, who is about to borrow or is aspiring to borrow that X. And here's the conversation. It's basically K says, if I give you access to X, can I trust that you won't change it? And B says, yeah, I promise I won't change it. And K says, you understand, though, that I might still be able to change X and give others permission. In other words, X isn't necessarily immutable. I'm just saying, I want B to promise you are not going to be the agent of change. B says, yeah, my promise not to change X doesn't necessarily mean no one else can change X. I understand that. And then finally, and this is also very important, you also understand you can't weasel out by asking others to break the promise for you. Yes, I promise I won't ask others to break my promise. Right? Because that's the ethics part. Is you say, hey, I promised I wouldn't do this damage. Would you do the damage for me? And then I can stand with a straight face and deny that I did it. Most of us would think that that's unethical. And that's basically the way const is handled in a C++ compiler. So let's apply it to this specific declaration. We have QC as a pointer to a constant t. What is the real nature of the promise here? The real nature is that the program says, I won't use any value obtained from QC, directly or indirectly, to alter any t objects. In other words, once the promise is made, the last part of the conversation says, and you can't hand it off to anybody else unless they make the same promise. So we can think of this, and by the way, this promise doesn't apply to other pointers, which if they coincidentally have the same value in them as QC, they're not subject to the promise unless they made it explicitly themselves. So that's the sense in which you can have an expression that designates a constant object actually referring to something which is really not const, really not immutable. So let's apply this reasoning to the function calls. So once again, we have this pointer PC, which is a pointer to a constant t. And that, in a sense, PC is the current keeper of the access. And now WP wants to borrow access through its parameter Q. But notice that Q makes no promise. That's a declaration that says, don't trust me. And so the compiler says, okay, I won't. And it rejects that call as an invalid pointer conversion. That's what you'll get. And the problem is that it's losing constness. So the compiler rejects it. And the problem is that if it were to compile, it would open up the door to violate the promise. See, it doesn't necessarily mean that WP will, inside its body, alter the thing it's pointing to, but it is saying, I'm not willing to swear to make that promise, and therefore don't trust me. Now, in contrast, when you call the function that wants a pointer to const, and you pass it something that isn't const, that's okay. Because what that's actually doing is adding a promise. It's not taking one away. And there's nothing wrong with somebody who says, I've got this thing that's modifiable. Can I give it to you with the understanding that it'll come back intact? I'm not giving up the right to change it or to give it to other people who want to change it, but I'm asking you, while I lend it to you, to not change it. That promise is perfectly legit. There's a name for this kind of pointer conversion. It's called a qualification conversion. And basically, it adds CV qualifiers to the type of that the pointer is pointing to. And so a more precise statement of what a qualification conversion involves is you've got a pointer to CV. CV1 represents some combination of const and or volatile. And CV2 also represents some combination of const or volatile, or both, or nothing. And we have this concept of a pointer being more CV qualified than another pointer if more CV qualified means that it has everything that was in the first one, plus it might have some more. So you can always add another qualifier, you just can't take one away. And so this same set of pointer conversions can be illustrated with assignments as well as parameter passing. So here we have P is a pointer to a non-constant T, and PC is a pointer to const. You can take a pointer to non-const and convert it into pointer to const because that's adding a qualifier on the pointed to object. But you can't go the other way, that's losing a qualifier. And by the way, the exact same rule applies for pointer to volatile. You can increase the volatility of the pointed to object, but you can't strip it away. And now here what we have is converting pointer to const into pointer to volatile. Well, that adds a volatile, but it loses a const. No good. Same thing, pointer to volatile into pointer to const. You're picking up a const, but you're losing a volatile. Not surprisingly, these things work with references as well, although interestingly, the standard does not refer to reference initialization as having qualification conversions. They just describe a set of reference binding rules which by some coincidence happen to be parallel to the pointer conversion rules. So here we have a function wi that wants an int and another one wci that wants a constant int. Once again, clearly you can bind a reference to an int and a reference to a constant int to a constant int. That's no change in type. But the reference initialization can increase the constness of the referenced object. So, for example, this one is perfectly okay. I have a function that wants a reference to a constant int, and I say, will you take a reference to an int? Yeah, fine, I'll take it, and I'll treat it as if it's const. No promise broken there. But if I try to take the constant integer and bind a reference that's not a reference to a non-constant integer, that's trying to strip it away. The compiler will not be happy with that. The standard, yes, if you have a question, please go over to the mic. I hate to make you step over other people, but it's a big room and we want to hear the question. Go ahead.
Can you go back to the previous slide, please?
Yes.
Where you say WCI, you can't bind a reference into constant.
Oh, that is a typo.
Yeah, that was
yes.
Okay.
Thank you very
Thank
much.
You.
Yes. That should have been I. And the miracle of PowerPoint is I can fix it right now so you can see the correct one. There. Thank you very much. Iterators. The standard library has a bunch of these container class templates, and they have members in them called iterator. Now, in the broad scope of things, iterator in the standard library is a generalization of a pointer. When you write algorithms, we try to write algorithms which will accept iterators that work equally well whether or not that iterator happens to be a genuine pointer or it's an object of a class type which is made to look like a pointer through operator overloading. Either way, that's an iterator. Well, but the standard container classes, the class templates like vector, dec, list, so on, they all have member types called iterator and const iterator. And those type members, the iterator type, for example, of a list is the type of an object you can use to essentially point to individual elements in that list. What's a const iterator? Well, it's you think of it as a pointer to an element, and what's the const doing there? It's actually a pointer to a constant element. It's not that the iterator itself is immutable, that you can't change it. It's that it's pointing to. So it's really, I would have preferred that the actual name would have been iterator to const, but that's not the name. You just have to live with the fact that const iterator is conceptually equivalent to pointer to const. Well, not surprisingly, since these things are mimicking pointers, you can do conversions between iterators and const iterators that mimic the pointer conversions that we just talked about. So here we have an example of a dec, and I've declared a dec of int iterator I and a dec int const iterator ci. Can you convert ci into I? No, because that drops a const from the pointed to type. But you can convert I into ci. That is the iterator type's analog of a qualification conversion. Now let's use these things in parameter declarations. Because one of the big questions that I think programmers are constantly asking is, Well, where's the right place to put the const? And I'll tell you up front, some ways are more useful than others. So here's the scenario. Suppose that you have a function foo, which has a parameter of type pointer to t, returns some value r. And a typical call on foo, you pass it an array. It's going to process the elements of that array. And when you use the array name x as an argument to a call on foo, you get that implicit conversion, array to pointer conversion. So let's now consider the consequence of putting const somewhere in the parameter list of foo. One way to do it is like that. Again, I could have said tconst const t, but most of you know I'm an east const guy, so this is I'm just showing you one of the two possibilities. So what's the consequence of doing that in terms of the behavior of foo? Well, foo is still allowed to alter p. It can use p to point to individual, so it can use p as a local variable, essentially, pointing in turn to the different elements within x. You can dereference p for the purpose of comparing it. You can increment p itself to be able to step to the next element. You can compare for equal, not equal. If it supports less than, greater than compares. These are all read operations through star p. But if you try to do that, you try to store into star p, try to alter any elements of the array x in this case, that's an error. And what I say is, this is a meaningful constraint on the behavior of function foo. This is an announcement that foo says, you give me your data. I don't care whether your data is modifiable or not, I'm not going to modify it. And when you look through the standard library, you see lots of functions that do this. They work equally well with constant and non-constant data being passed in because they say, I'm going to treat it like it's const. If this is the behavior you want, this is the way to get it. How about this? Putting const on the pointer itself. What does that say? What this says is inside the body of foo, you can't alter p, but you can still use p to, in this case, alter the value of the 0th element of the array. Right? Because p itself is constant. It can only point to the thing that it's initialized to point to, which in this case is x sub 0. Now, my reaction to this is, I'm nearing retirement. In 40, actually it's not quite 40, it's almost 40 years of C and C++ programming. I can't recall ever wanting a function where that was the behavior that I wanted. I would claim that this is pretty useless, if not deceptive. Because I think when you're looking at the declaration of a function and you see a const there, most programmers are going to say, I want to know what you're going to do with my data. I'm handing you some data. What are you going to do with it? And what does this const say? This const basically says that I am going to take the copy of the address of your data and I promise I won't change it. I won't change my own copy of your address. And I say, gee, thanks. Thanks for sharing that. But it doesn't affect what foo can do with my data. Foo can go ahead and scribble all over my data. Do it like this. So you can take the value in p and copy it to q. Notice that q is no const there in q's declaration. Hold it, isn't that going to violate something? No. Because p is a constant pointer to non-constant data. And I'm taking that constant pointer and copying it. The value being copied is a pointer to t. A pointer to non-constant t. The only thing I promised here was I wouldn't change p itself. That doesn't change P. And then I can go ahead and use Q to scribble all over the data that was passed in. You can also do it with array notation. You can declare a local variable for an index and a subscript off of the point, and that doesn't change the pointer either. So I would say I'm not too partial to using const in this way. I think it's arguably deceptive. You know, it tricks the less than completely alert reader into thinking that there is a behavioral statement there when there really isn't. There's an implementation statement, not a behavioral statement. How about this one? Well, that's overkill. Because the const that modifies the T has an effect on the outward behavior of the function. The const that modifies the pointer, well, we just dismissed that one. So my advice to you is you declare a pointer parameter as pointer to const if the function shouldn't alter the pointed to object. And that imposes a meaningful constraint on the function's outward behavior. The guideline for references is similar. It's declare a reference parameter as reference to const if the function shouldn't alter the referenced object. And we see abundant examples of this in common class member functions like copy constructors and copy assignment operators. It's exceedingly rare. I hate to make absolutist statement, but you don't really want these to be destructive copies, which is what you would get if you took the const off there. The potential that the source operand would be modified by copying it. Now, I need to introduce a little bit of terminology to be able to talk about the next concept. It's that in C++, as you well know, data types can exist on multiple levels. So for example, when you declare a pointer to character, it's a two-level type, pointer to character. When you have an array of pointer to int, it's array of pointer to int, 3 levels. And when you just say a type is string, that's 1 level. And there's this term for a CV qualifier applied to the first level. We call it a top-level qualifier. For example, here, this is P is a constant pointer to a T. Const is the top-level qualifier. Q is a volatile pointer to a constant T. Volatile is the top-level qualifier. These don't have any top-level qualifiers. Even though P is a pointer to a const volatile T, there's no qualifier on the pointer itself, which would be the top level. So what about top-level types in parameters? Like this. Here's a function g that takes an int. My position is, my advice is, regard this as useless. And the reason is, it's already passing by value. When you have an integer argument n, and you pass it to g, g's making a copy. That's what pass by value means. And so g can't alter n. And the presence of the const there doesn't make that inability any stronger or weaker. All it does, again, is it affects what g can do with its copy inside the body of the function. And so I tend to discourage this. Yes?
So the argument that I've heard in terms of this is there's a difference between whether it's on the interface or whether it's on the implementation.
Yeah, hold still on that, yes. Okay. I don't mean to cut you off, but I'm getting there. Yes. So here is the thing that I caution about is, here a familiar function, memcopy. And notice that there is a const in the parameter list on the source operand. It says S is a pointer to a constant void. Notice there's no const on the destination. And there's no const on the size t parameter n, which represents the number of bytes to be copied. And it's a common idiom to implement this by decrementing n inside the function. So what's the consequence, for example, of putting const there? What it does is it renders this particular programming style invalid. You're now obligated to copy n to another local variable in order to be able to decrement it. I'm not sure you gain much by doing that. And to make matters worse is, well, if you're going to put the const on the size t, then let's look at the other top level types where you could put it. You could put a const on the return type, on the parameter d. You can add another one to the declaration of s, and you can put one on n. And I've put them all in red because they don't affect the outward behavior of the function. There's only one of those 1, 2, 3, 4, 5 consts that actually has a substantive impact. And the problem is, once you start going down this path, most people regret it, because what it does is it drowns the meaningful consts in a sea of relatively meaningless consts. So you should use it proactively, but I believe you should avoid using const at the top level of parameter declarations. Okay, and I haven't forgotten about your point. Okay. Okay, let's just talk for a moment about const and class design. And I'm going to use as my illustration a rudimentary string class that looks a lot like the standard string. Here's a sketch of an implementation. The private data consists of a pointer to a character that points to a dynamically allocated array that holds the text of the string, plus an integer, which is the current number of characters in the string. And you have some member functions like size, which is how you ask how many characters are currently there, and there's a member function clear, which will erase the contents of a string. Now, it's very typical that you pass string objects by reference to const rather than by value, because passing a string by value invokes the copy constructor and makes a copy of the entire string. Generally expensive thing to do, so the prevailing wisdom is, unless you really need a copy, you pass by reference to const, because it has a very similar effect outwardly, namely, I'm giving you access to my string without having to make a copy, and you can't modify it, which is what would happen if you passed it by value. Something that looks like that. Now, the problem is that that code right there, based on everything I've shown you, won't compile, and the reason it won't compile is because the compiler will complain about the call on the member function size. And that's because the declaration of s in the parameter list of foo says, I promise I will not alter s. And now here you are passing it through a this pointer to a member function, and it's perfectly legitimate to ask, well, where's the promise that size made that it won't alter the string that it's computing the size of? I didn't see anything about that. Well, now, if this parameter were explicitly declared in C++, solving this problem would be easy. You would just throw a const into the explicit declaration of this. And that's how size would make the promise. But those declarations for this are not something that we write. The compiler writes it for us. So where do you squeeze the const? And the answer is, you put it after the parameter list. That's the way that a function says, I promise I won't alter the object that my this parameter is pointing to. It has the effect of modifying the declaration of this to be a pointer to a const. And one of the consequences is then that inside a const member function, any attempt to modify a data member of the object is now rejected as an error, because this is pointing to a constant object. It keeps the promise. And so if you try to put the const on the clear function, though, you'll find you're getting carried away here, because it's really hard to clear a string and say, but I promise I won't alter its contents. And you'll be called out by the compiler for doing that, because it will reject attempts to modify data members of the object inside the body of the function. So the rules for passing const and non-const objects to member functions are direct parallel to the qualification conversion rules. So you can apply a const member function to either a const or a non-const object. But you can apply a non-const member function only to a non-const object. So think about it this way, is that if you're writing classes and your attitude is, I can't be bothered putting const in the interface to that class. I just don't want to fuss with const member functions. The consequence is that anybody who wants to use your class can't declare constant objects. They could declare const objects of that type, but as soon as they try to apply any operations to it, they'll be rejected by the compiler. On the other hand, if you opt to use const as you're designing the class and implementing it, you don't force anybody to use const. You say, the freedom is yours. Make objects const or non-const, and I'm going to give you full functionality for those objects. And so the advice is declare a member function as const whenever it's meaningful to do so. Now, I have 3 minutes left, and I wasn't sure exactly where I would end, so this isn't quite, bear with me just another few minutes. I'm going to do a few more slides. There's a curious flaw in const member functions, and that is right here, is that if we implement a square bracket operator to illustrate this point, let's go ahead and add it. And I think square bracket should be a const member function, because if it's not a const member function, you can't select an element out of a constant array, like out of a constant string. You want to be able to do things like that. And when the compiler sees s sub I, it will interpret it as s dot operator square bracket of I. And the implementation looks something like that. Very simple function. Notice it's a const member function. It says I won't alter anything. But look at the return type. It's a reference to const. It's a reference to a non-const character. What does that mean? It means that you could write code like this. You could say, I've got a constant string, and I'm going to assign to it one of the characters in that string. That code would compile. And I think most of us would say that's a logic error. And the reason it does work is because it's returning a reference to non-const, a modifiable character. And this is illogical. The reason it's illogical is because most of us expect that an element selected from a constant string should be const. Oh, and by the way, an element selected from a non-constant string should be non-const. Right, that's the logic. So why does that even compile? And the answer is that this, in a const member function, is pointer to const. Actually, it's a const pointer to const, but let's not go there. What matters is that when you're in a const member function, it makes the top type of all the non-static data members const. It's like this. The const is applied not to the contents of the string itself, but to the pointer that points to the string. Okay? And that's why the code goes ahead and compiles, because even in a constant string, the contents of the string are non-const. What we really wanted was this, but that's not what a const member function gives us. And so the thing to do is to repair the return type. You just have to fix the flaw manually, like this. Now, for reasons of time, I'm going to just skip ahead and show you. The problem is that it prevents you from modifying a string that you want to be able to modify. You could cast it away, but that's not where we want to go. Here is the proper solution, which is to overload them as const and non-const so that you get logically consistent return type behavior. That is, an element selected from a non-const string should be non-const, and an element selected from a const string should be const. And so it's really a special case of doing this. You have you can overload functions on pointer to const and reference to const. And this is the answer to the question that I cut off, which is that when you have a const in the parameter type like this, most of the time it's part of the signature and you can overload. However, the top level qualifiers don't participate in the signature, so it means that this is not overloading. This is two declarations for the same function, and the const is ignored for overloading purposes. And some people like to take advantage of this and say, well, I will declare the function without the const and define it with the const because that's part of the implementation. I'm not too partial to that style, but I'm not going to argue vehemently against it as being wrong. I do think, though, it creates a lot of, you have to educate people a lot to get them to use that style. Okay, so that's not an error, that's just a redeclaration. This is overloading, but this is not. So the placement of const in or out of the declarator makes all of the difference. And now I'm really done.